You may recall at the beginning of our polar unit that we looked at a point. It was actually the point 68. And we discovered that there definitely is another way to describe that location. Yes, indeed, you can describe that location using r and theta. It turned out that all we needed was a rotation of 53 degrees and a radius of 10. And of course, we had the same point. Well, it would seem that we should be able to convert between these two types of notations pretty comfortably. You see, when you have x and y, that's called rectangular. Those are rectangular points. For obvious reasons, we describe the location with a rectangular movement. But when we change to r and theta, of course, we call that polar notation. So how do you convert between the two? Well, do you remember when we had x and y? All we had to do was find the radius. And of course, you can find the radius using the Pythagorean theorem. And then, well, we also had to find the angle. And to find that angle, all we needed was a little bit of trigonometry. Is there more to this concept? There is, but there definitely is not less. And so what we're going to do today is using your little graphic organizer, we're going to basically learn how to convert back and forth between polar and rectangular using points and equations. Now, this is a pretty loaded lesson. It does take about a full 40 minutes, but the nice thing is with the video, you can pause it. You can even play it faster if you need to, just to make sure that you get all the learning. But make sure you find your graphic organizer. We're actually going to use the back of it to do a little discovering, and we're going to use the front of it then to kind of end up with our official notes. So we're going to start on the back. We're going to do some scribble and scratching to basically kind of discover, perhaps once again, how to convert from a rectangular point to a polar point. So what we need is a rectangular point. How about we'll use a different point this time. We'll use the point 6, -6. Now that point 6, -6 is definitely an x and a y value. And so perhaps with a simple sketch, we can start to explore what is true about this. And so if I plot 6, -6, and then proceed to think about the radius, well, not too much, not anything too tricky with that. The radius of that point is going to be nothing more than just the Pythagorean theorem of our x and y value. But to kind of see that worked out, you're definitely going to end up with the radius squared equaling each of my x and y values squared. And of course, on a good day, when you square something, it always comes out positive. So we're going to end up with 36 plus 36 equaling 72. And when you take the square root of both sides, of course, you get the square root of 72. Or if you prefer, you can take out that perfect 36. When you take out 36, you, of course, just get 6, leaving behind the square root of 2. So we can write that as 6√2, or as you'll find, we can also get the decimal value, which is about 8.49 for your radius. Now your angle theta, now that might require a little bit more pause here because this time I'm going to need some trigonometry. Now remember, the trigonometry would simply be right triangle trigonometry, and I believe we have an opposite, which of course is -6, and an adjacent, which is 6. That sounds a lot like SOHCAHTOA, so I can set up a nice tangent statement equaling opposite over adjacent. Now that means that the tangent of theta equals -1, and if you do a little bit of inverse tangent, of course the inverse tangent on your calculator, you would end up getting, so we end up with -45. Now, the nice thing about the ordered pair I gave you, 6, -6, is that it's definitely part of a really nice 45-45 triangle. And so we can see that the Pythagorean theorem definitely will give us our radius, but the -45 can already be confirmed by of course, again, the values in that triangle. So how did we actually end up converting from rectangular to polar? Well, if you flip your notes back over, we can kind of summarize that we indeed used the Pythagorean theorem to find the radius. And I'm going to give the formula to you already solved for r. I'd like you to see the square root of x squared plus y squared. Of course, that does not simplify, but rather you just do the sum of x squared plus y squared, and then you do the square root. And I'm also going to give you theta solved with the inverse tangent of y over x. Of course, that was the opposite over adjacent. Leave a little bit of space right here. You're going to find out that we end up filling one more thing into this box. But what I'd like you to do is I'd like you to kind of test this, this method, these two formulas. I'd like you to test it with the point -3, -5. This will be a good time to pause the video because you actually want to try to do the problem, and then I'll meet you back here when you're done working it out. May I say, proceed with caution on this problem. Something might be a little bit special. So pause the video and go ahead and see if you can convert it. All right, so how did you do? I would assume that you pretty comfortably plugged in to the Pythagorean theorem. Of course, I did give you two negative numbers, nothing too terribly tricky. Make sure if you're using your calculator that you're using it correctly. Better yet, you can just square this and get the square root of 34, which again, you may leave your answer in that form. If you did turn it into a decimal, which is fine also, you would get 5.83. How about theta? The inverse tangent, again, it's already solved for theta, so the inverse tangent of -5 over -3. You know, of course, that those two negatives are going to cancel, but either way, we end up with a little bit more than 59 degrees. Is that right? Right? Wrong. Wrong? What do you mean wrong? We used the formulas that we sort of discovered on the back. Well, let's take a look at the sketch. Okay, let's take a look at the point -3, -5. Okay, it's just a little sketch, but that kind of gets me in the ballpark of this space. Again, that's the point -3, -5. Now, if I think about the radius, since it's just a sketch, unless I have like a ruler or it's drawn to scale, I have to pretty much assume that the square root of 34 would be that distance, and it is. But if you look at the angle, 59 degrees, 59 degrees, 59 degrees, I'm pretty sure that that is over here. Wait a minute, that is on the opposite side. Now, how can I take my angle of 59 degrees and sort of make it right? How can I make it so that I end up over here where the point actually lies? That's right, you can take 59 degrees and you can add 180. Now, if you add 180 to it, you end up with an angle that actually makes sense. You end up with 239 degrees. Now, is 239 degrees going to rotate you all the way over to this point? Indeed, because I'm going to start at 0 and I'm going to rotate over here 239 degrees. So that'd be one way to sort of fix my answer. And let's kind of be clear here. What is the answer? It's a point. So the square root of 34, but 239 degrees. And again, that polar point would be indeed in the same location as -3, -5. But there's another way to fix my point, and it would be, once again, thinking about being on the opposite side. You see, if you do rotate 59 degrees, if you really like 59 degrees, all you'd have to do is make your radius negative. In other words, if you make your radius negative or the opposite, and you stick with 59 degrees, then you also would be in the same location. So what happened here? How come we had to fix our answer? Well, it wasn't because we made a mistake. It was actually because x was negative. You see, when x is negative, You can do the inverse tangent of y over x, but you're going to have to add 180 degrees. And again, that's when x is negative. But when x is positive, well, we're good. We can just basically do the inverse tangent. Now, we also fix the answer, or you might say we could fix the answer by doing the opposite of the radius. I'm not going to put that in the notes here. It just kind of gets a little bit too busy. But if you understand that, you can make the radius negative and you can keep theta, and that would be another alternative. And that's when x is negative. I wonder what you do when x is equal to 0. Notice that the notes don't talk about that, but you're going to get a chance to try that on the homework helper. Let's flip over to the back and we'll do a little scribble and scratching. This time, we're going to think about converting the other direction. This time, we're going to start with r and theta. This time, we're going to start with a radius and an angle, and we're going to see if we can figure out how to go backwards to x and y. Now, you might think that it's just backwards of what we did in the previous example. Not quite. It's not quite that easy just to kind of like reverse those rules. What we need to do is basically develop this a little bit. So, of course, if we have an r and a theta, they would no doubt be represented by this distance and this angle. Remember, if we're converting it to rectangular, that would mean that we would want an x and a y. So, well, from the familiar sketch, x and y can 100% be the legs of this triangle. So the question now becomes, how can you take an r and a theta and come up with an x and a y? Let's talk about y. Let's talk about the y value first. Now, the y value is opposite my theta. And the radius, of course, is the hypotenuse. And so I'm hearing that drum again. I'm hearing the sine trig function, which uses opposite over hypotenuse. Now that sine function, of course, has always been true since day one. But if you solve that, if you rearrange that for y, then you can make a statement that would say that r sine of theta equals y. And if you look at this, the two things that are part of my statement would be my two givens, because I would be given r and theta. So what about x? X. Right, it's beside theta. It's adjacent to theta. And of course, that familiar trig function, the cosine of theta, well, it relates x with r. And if you take that function, if you take that statement and you solve it for x, you would get r cosine of theta. What we end up with are two formulas. And these two formulas can be used to find x and y. Let's go back to the front of the paper. That's 100% what we're going to put in our little method box. Of course, I'm on the right-hand column now because we're converting polar to rectangular. And so x equals r cosine of theta and y equals r sine of theta. As you're writing that down, I got some good news for you. There's no funny business. You don't have to worry about positives or negatives. You honestly can just plug right into those formulas. Why don't you give it a try? Why don't you convert 6 negative 100? I gave you a negative just so you can test it for sure. Why don't you convert that to a rectangular point? Another good time to pause the video, try the problem, and I'll meet you back here in a second. All right, so how did you do? It's pretty straightforward. You just plug in 6 for r, and you plug in negative 100 for theta. Of course, if you're trying to find x, it's going to be 6 cosine of negative 100. Use your trusty calculator, and you end up with a little negative 1.04. Y value? You got it. Just plug into r sine of theta. So we got 6 sine of negative 100. Calculator to the rescue, and out comes negative 5.91. Now remember, this is a point that you found. It's actually a rectangular point, but nonetheless, we need to write it as a point. And so we'll put it as an ordered pair, negative 1.04 and negative 5.91. We'll just kind of squeeze it right there. Now, I told you that there's no funny business with negatives, but did you believe me? Why don't we just double check this? Basically, why don't we graph our polar point? Of course, we're going to graph it on the polar axis. So why don't we graph our polar point 6, negative 100. That would mean that you have to rotate negative 100. And that'd probably be about right here. So we're going to graph our point. We're going to count out 6 units. It's just a sketch, but that'll put us about right there. Again, this is my original 0.6, negative 100. Now, with just a little bit of basically observing, I can see that it makes 100% sense to say that the location of this point would have a negative x value of negative 1 and a negative y value of negative 5.91. We're good. You can trust these two formulas. They work every time. Now, if we were in class, what I would have you do right now is just pause and kind of summarize with your partner, how do you convert from rectangular to polar, and how do you convert from polar to rectangular? What I'd like you to do is just pause and either reflect with yourself, or if you are doing this with a neighbor, just take a look. How do you convert in both directions? Because in a moment, we're going to do this with equations. And guess what? We're going to end up using a very similar strategy. Go ahead, summarize the two methods. All right, some funny, awkward silence. Did you look at your two methods? Because now what we're going to do is we're going to flip her back over to the back, and we're going to take a look at how to convert an equation. Okay, now I'm on the back of the paper on the left-hand side, and we're going to take an equation. We're going to take the equation x squared plus y squared equals 9. Now just kind of notice that's a rectangular equation simply because it has x and y. And we're going to try to convert that to polar. Now maybe you're saying, okay, Ms. Naylor, but I don't know the equation x squared plus y squared equals 9. No, this could be the very first time you've seen an equation like this. I can promise you it won't be the last. Now, in order to understand this equation, what we're going to do is we're going to graph it. Honestly, we're going to graph it on our calculator. And when you graph it on your calculator, all you got to do is solve it for y. Now, we're just going to do this mentally or sort of verbally. To solve this equation for y, you got two things you need to do. You would subtract x squared from both sides, so you get 9 minus x squared, and then you're going to take the square root of both sides. And so when you take the square root, you get the square root of 9 minus x squared. Don't try to simplify that. It's the square root of 9 minus x squared, with one extra caveat, plus or minus. And so I'm going to type that in my calculator as two separate equations. Notice that I typed in a positive square root of 9 minus x squared and a negative square root of 9 minus x squared. Now, when you graph that on your calculator, you end up getting a pretty neat graph. You get a pretty neat shape. Okay, now depending on if you changed your window, I'd made my window so it's a little more square. So depending on if you changed your window, it may not look perfectly, but it's supposed to be perfectly circular. It's a circle. But the point here is that x squared plus y squared equals 9 is a circle. Oh, great. Those are the kind of equations that we've been talking about in polar land. And that means that we can write it as, as a polar equation. Okay, now if you look at that circle carefully, you should deduce that it has a radius of 3. How do I write an equation for a circle that has a radius of 3? You got it. R equals 3. Now this is always the part of the lesson that's a little strange because we converted it. We did it. We converted it to R equals 3. Okay, but we converted it by using a little bit of some technology and kind of just observing the graph. Okay, you might say we used a graphing method. What if I want to do this more algebraically? You say you don't. You do. You want to do this algebraically. And I've got good news for you. All you have to do is use formulas that we discovered on the front of the paper. You see, on the front of the paper, I'm pretty sure we had a formula for x. It was r cosine of theta. And I'm pretty sure we had a formula for y. It was r sine of theta. Guess what? We can substitute both those formulas in there for x and y. Okay, now notice I'm substituting into my rectangular equation. So the letter x is going to disappear, and it's going to become an r cosine of theta. The letter y is going to disappear, and it's going to become an r sine of theta. Okay, now this is an algebraic method, and before you get too grumpy, you're going to need this to be able to do some other problems. So let's continue. Continue doing what, you say? How about some algebra? Okay, here I can legally square both of these, basically both these variables. That's because it is a multiplication problem, and so I can legally bring in the square. I get r squared cosine squared plus r squared sine squared, and it still equals 9. Now, try not to lose sight of what we're trying to do here. We're trying to come up with an equation that is in polar, that is polar. And I definitely have some polar stuff here. I've got r's and thetas, but I feel like that it can be simplified. Don't you agree? You could factor out a 9. Now, you could factor out not a 9, but you could factor out an r squared. Now, if you factor out an r squared, you are left with cosine squared plus sine squared. Cosine squared plus sine squared. I know, it's hard to get your eyes off of it, isn't it? It's so beautiful. Look, it's our Pythagorean identity. And what does cosine squared plus sine squared equal? That's right, it equals 1. And then that leaves me with just r squared equaling 9. But if you simplify that, if you basically take the square root of both sides, bingo, you get r equals 3. Now, just make sure you realize that r equals 3 was the answer a few minutes ago, but now we found it using algebra. And what that kind of proves to us is that if we substitute, like we did in blue right here, if we substitute r cosine and r sine, we can end up with a polar equation. Flip her back over to the front. I'm on the left-hand side, now down to the equation section. And what we're going to do is we're going to conclude that we're going to replace x with r cosine of theta. And we're going to replace y with r sine of theta. And when you do that replacement, you're going to end up with a polar equation. Now, equations are a little more varied, aren't they? There's kind of like more options. So we have a couple more examples to work through here. When you're ready, we're going to convert y equals 3x, which, just note, that is a rectangular equation. It's got x and y. We're going to convert that to a polar equation. How are we going to do that? We're going to replace y with r sine of theta, and we're going to replace x with r cosine of theta. Now, this looks a little different than the circle that we got on the back. I'm pretty sure it's not going to be a circle, but let's try to simplify it. Let me suggest that the sines and cosines would do a lot better if they were together on the same side. So what we're going to do is a little algebra. We're going to divide both sides by the r cosine of theta. If you say, how was I supposed to know that? Well, why don't you take a look at what happens, because I think you'll say that next time you'll want to do the same thing. See what happens? The r's cancel out. I end up with sine over cosine. Wait a minute, sine over cosine, that's equal to tangent. That's correct. I end up with tangent equaling 3. And it turns out that since tangent equals 3, that if I do the inverse tangent, remember, anytime you do an inverse, you always get an angle. So if I do the inverse tangent on my calculator, now that'd be the inverse tangent of 3. I know it's kind of a strange, just the inverse tangent of 3, but trust me, if you do that, you probably should try it. It's kind of cool. You get an angle. You get 71 degrees. And if you think about it, y equals 3x from the beginning was a line. It was a line that had a slope of 3. And if you think about it, 71 degrees, where that is theta equals 71 degrees, is also a line that matches perfectly. So we converted a diagonal line, that is a line that has a slope, to be an angle. What about a horizontal line, like y equals -5? What if you convert y equals -5? Okay, now, again, that's a horizontal line if you think about it, but it's kind of cool. You can still substitute r sine of theta in here for y. Okay, now, again, this looks a little different than the previous two problems, but I'm going to help you out here by saying that if we divide both sides by sine, now the reason I want to do that is because I want to write my answer as r equals. Now, when I have -5 divided by sine, I would legally be able to flip that sign up to the top and rewrite that as a cosecant. It's a little bit more simplified, -5 cosecant of theta. Let's do one other equation, which you got it. It's different than the other two. It's x squared plus y squared equals 16. Now, x squared plus y squared equals 16, that kind of looks like the x squared plus y squared on the back of the paper. Do we need to substitute in r sine and r cosine? Sure. I mean, we can, but we can also be ready for a bit of a shortcut because now, can we substitute r cosine and r sine in for x and y? Sure. But if we substitute those in, we may realize pretty quickly here that there definitely is a shortcut to this type of problem. Because every time you factor out the r squared, you're going to be left with cosine squared plus sine squared, which of course is equal to 1. And so I'll end up with r squared equals 16 every time, which means that r equals 4 every time. In other words, I'm going to end up with a circle. And so whenever you have a formula of the sort of the style or the sort of the form of x squared plus y squared, well, that is always going to equal the radius squared. In other words, x squared plus y squared equals r squared is always going to be a circle with a radius of r. Am I saying that you could take x squared plus y squared equals 16 and you could just in 5 seconds write r equals 4? I am saying that. You may use that shortcut as long as you understand that this is a circle. Okay, but if you substitute in the blue r cosine and r sine, it'll work every time. And those are the things that you're going to keep working through as you process this lesson, especially tonight with your homework helper. All right, we're ready for the last category. And you know what? We're not going to flip over to the back because we don't really need to. Instead, I really just need to tell you that for this last category, when you convert polar back to rectangular, actually what you need to do is recognize. You need to recognize the category. Basically, these 3 types of problems are going to just require you to kind of reverse a bit of what we did on the other side, and you'll be able to reverse that when you recognize the type of problem that you're given. So one of the types of problems that you're going to be given is going to be a line. And when we say that, we're talking about a line that has a slope. So for example, if I have theta equals 240, now keep in mind theta equals 240 is a polar equation. Of course, it's a polar equation that is basically a line. It's a line that is represented by an angle or a rotation of 240 degrees. Okay, so if I start on the polar axis and I rotate 240 degrees, I get a line. Okay, the real question here is, how do I write this equation using a slope and a y-intercept, basically using y equals mx plus b? Okay, let's kind of develop this a little bit here. First of all, it wouldn't be wrong to sort of put the x and y axis into your sketch because that's what we're trying to convert to. Nice thing about putting the x and y axis in your sketch is it allows you to kind of see a little bit more clearly what we would consider to be the slope of the problem. Okay, now the slope of the problem is, of course, remember, is the rise and the run. And I feel like that the rise and the run are actually parts of a right triangle. Now that right triangle is no other than a right triangle that has 60 degrees. Just doing a little bit of thinking about 240. And wait a minute, you know the dimensions of a 60 or a 30-60 type triangle, right? You know that on this side, that is the side across from 30, you're going to get a 1. And you know on this side, you're going to get a root 3. By the way, the hypotenuse would be 2, but we don't really need that. So we end up with a rise of root 3 and a run of 1. Sort of. Technically, isn't this actually a -1 and a negative root 3? Well, technically it is. But nonetheless, my rise and my run are basically the sides of that triangle. So I end up with a slope of negative root 3 over -1, which of course simplifies to be root 3. Now remember, the reason I'm trying to come up with a slope is because I want to write an equation. And so an equation of the form y equals mx plus b, now that looks more like it's been converted. By the way, the b value is the y-intercept, and just to make sure we know that that is 0. So we've got our equation. I know what you're thinking. What if the slope is not part of a special triangle? Okay, well that's going to be something that you're going to keep working out a little bit on your homework. And I'll sort of give you a hint. You're going to want to think about some formulas that we had up above, because formulas that we had up above are able to still give you x and y, even if they're not special. Okay, but that's how you convert a line. Let's do the next category. Let's do a circle. Okay, I guess for some reason I have that as my second example. So let's do a circle. How about something like r equals 12? Now again, the important thing to realize is that is a polar circle. So if you want to convert a polar circle to a rectangular circle, you're just going to need the x squared plus y squared formula. Remember, x squared plus y squared is always going to be a circle. Now I got a question for you. Is it going to equal the square root of 12? Is it going to equal 12? Or is it going to equal 12 squared? It's definitely x squared plus y squared. But is it going to equal, well, is it going to equal, you see, you just got to believe it's going to equal the radius squared. So if I think about it, the radius squared would have to be my third option here, represented by 12 squared. And so when I write this answer, I can write 12 squared, but I'd prefer that you simplify it to be its value. And so x squared plus y squared equals 144. That's going to be your converted equation. Just kind of note, there really wasn't any work required there. The only work was to realize that you have to use that formula. And basically, if you plug into it correctly, bingo, you got your equation. All right, there's one other type of equation. It's kind of represented by a conversion formula. What do I mean by a conversion formula? Well, basically a formula in the form of r equals a trig function. So it's different from the other two. It's a conversion formula. What you have to see here is that the secant, it really would rather be on this side. At least if it's on that side, it makes it a little easier to see the formula. Now, if I divide by secant, I can write it as r divided by secant. But remember, when you're dividing by secant, that's the same thing as having a cosine. So I divide secant to the other side, but I sort of change it back into cosine because that's what it wants to be. That's because our cosine is a conversion formula. What do you mean a conversion formula? Well, I'm pretty sure up above, we know that that equals x. And so if I change it to x, and when I write it as x equals -2, then I've converted it to a polar equation. Now what you need to do is definitely take some time and process these different methods. You'll find a really robust homework helper. It's got a couple examples of each type. Make sure you know what direction you're converting, and we'll keep working this out. We'll actually practice this even a little bit more tomorrow. But for today, that's all I got for you.